Thank you, Mr. German. Thank you for coming to my talk. Indeed, I'm going to talk about the relations between structured bonding properties in two unrelated but actually interesting solid-state systems. The motivation for our study is that after over 100 years after the serendipitous discovery of superconductivity, we found tens of thousands of superconducting materials with varying degrees of novelty, let's say. Most of them are available in the SuperCon database, which is currently sadly down. We pretty much still have no design principle to rationally find new ones, right? So we do have the BCS theory, which explains the macroscopic mechanism behind electron bonding superconductivity, but it does not give any materials-related knobs that we can tune. At least not any obvious ones. And in the area of the materials-related theory, we did develop some heuristic rules. And the great example is Matthiesen rules, which were mentioned by Professor Predicting, my former boss. And actually also my mentor. So Matthiesen was a superconducting hunter in the 50s and 60s. He found superconductivity in a number, tens or hundreds of different metallic alloys, and he was able to plot a Tc versus valence electron count relationship, and he found that actually superconductivity tends to be suppressed at opposite electron counts. We will come to that point in a minute. Or we can do maybe some machine learning based on some structural features or chemical features, electronic structure descriptors or whatever. It kind of doesn't work though, because since we do not know what to search for, we can we're unable to force the machine learning algorithm to search for reasonable superconducting systems. Basically, they discover what's already discovered. Oh, that doesn't work. So, the heuristic, the development of those rules can be a great analogy for that is some collaborative projects like, for example, OpenStreetMap. So, OpenStreetMap is a project in which people like just don't understand normally internet users can map their surroundings. They added a global map which is pretty accurate in some areas, pretty inaccurate in some areas. For example, there is no hotel here because there was no one just working in the area. So reasonably, no one can map the whole world, but maybe they can map or help mapping the neighborhood and then draw some conclusions, draw some connections to the other neighborhoods. And that's exactly what we do here. So a great example of that kind of approach is by our collaborator from currently Michigan State, if I'm right, Professor Winiarski-Faculty, who's like 7 years ago published a study on gallium and endohedral superconductors. Kind of exotic system with about 10 different compounds reported at the time. Most of them are superconducting. It's a whole zoo of rather complicated structures. These are just like those three drawn here as just those that can be drawn in a way that you can see anything. So, for example, molybdenum 6-gallium-31 is a triclinic system with very large volume, like 136 different atomic sites. It's a monster, but they can be kind of put in one context by plotting the Tc versus some electron count. Because they share some common motif, some common electronic structure motif, which is the corner or edge sharing transition metal centered gallium-9 or gallium-1 clusters. Okay. So when a chemist hears a thing like magic number behavior, there are three names that will ring in his head. First is Kenneth Wade and the Wade-Minkos rules, which describe conductivity and bonding in clusters. They are originally that was boron clusters or Wade clusters, and so as we tune the electron count by either doping replacing some boron atoms with carbon or with hydrogenating and whatever, we change the conductivity because the bonding tries to the electron bonds arrange themselves in a way to optimize the bonding to decrease the number of anti-bonding or electrons. Okay, and it's a general rule for covalent materials. The other two names is Young and Teller, because you're probably all familiar with Young-Teller effect. Young-Teller effect is a phenomenon in which there is a large electron-proton coupling coming from some electronic configuration, some discrete electronic configurations in covalent systems, effectively, at which electron movement is associated with some distortion, so phonon mode, which leads to the distortion. In a metal, that distortion can be some kind of arrested because the localization energy, the bandwidth energy scale may dominate the energy gain from distortion. Okay? So in a metallic system, the Young-Teller effect can be kind of non-static and it will form some kind of soft modes but will not result in complete distortion. The question is how we measure chemical bonding in solids. Chemical bonding is a local picture of a solid. We are used to delocalize, think of solids are completely delocalized things like electron bands, right? So we have a tool that was developed in the 1990s by Richard Jankowski from Aachen, Germany. It's called crystal orbital Hamilton equation. It can be considered as a bonding weighted density of electronic states times some bonding energy. The COHP is negative for bonding states because the energy is negative for the bonding state. So we usually plot negative COHP and then it's going to be positive for bonding states. We usually plot it against the energy. It can be also plotted in a K-resolved case if needed, right? And it was shown that tuning the electron count into the antibonding states of shifting from level into antibonding states, so effectively inducing the antibonding population, will lead to structural distortion. Of course, it's a great paper which describes the tellurium structure based on the Young-Teller distortion of a polonium structure. Okay? Ferromagnetism. So Jankowski et al. Has published a series of papers in which they were able to rationally make a material ferromagnetic by tuning the electron count, only so just pushing the Fermi level into antibonding regions. Great. So how about superconductivity? After all, structural distortions grab some kind of states. They remove some states from the Fermi level, depopulating the antibonding states. Ferromagnetism splits the band, splits the density of states into, and then decreases the antibonding population. So how about superconductivity? Maybe we can just take those troublemaking electrons and then just gap them out by forming Cooper pairs. So it's a figure from our paper actually from 2 years ago. An example of such a phenomenon is found in those two carbides. These are sodium chloride type carbides, hafnium carbon, which is non-superconducting down to like 0.01 Kelvin, and the tantalum, which is just one electron over, which has a DC of 10 Kelvin or so. So we pushed additional electrons. Now the Fermi level lies in the antibonding region and superconducts. Great. So get back to the endohedral clusters case. Vanadium 8 gallium 41 versus molybdenum 8 gallium 41. Both very complicated structures. One's not superconducting down to well below 2 Kelvin. The other one has DC of almost 10. Great. So they only differ by just one electron per transition metal. And the structures are the same, the connectivity is the same. So the extra electron is occupying the antibonding state. Sorry for the figure, I thought it's going to be bigger, but effectively there is a small number of antibonding states at the Fermi level, great, which increase the electron coupling, make them superconducting. If you increase the electron coupling, the electron count even further by replacing molybdenum with rhenium, the structure would change. The crystal structure would rearrange to optimize bonding, but not completely, so it's still also a superconductor. There's a discussion of that same topic in the same group in a couple of papers by Winiarski-Faculty, et al. So if you're interested, you can just check it here. Moreover, we discovered superconductivity in palladium gallium 5, which is just below 2 Kelvin. It was overlooked for years. Here also, the density of electronic states at the Fermi level is composed mostly of anti-bonding states. Okay? And it turns out, with some new additions to the endohedral gallite family, we can plot a larger phase diagram, let's say, by plotting actually DC versus valence electron count in the atom, because here, as you can see here, the density of states at the Fermi level is the contribution of palladium is negligible. It's small, well, maybe not negligible, but because of the anti-bonding characteristics. Great. We don't know what lies here. Yeah, so some doping experiments would clear that maybe. Moreover, we recently showed that ruthenium aluminum 6 is a superconductor with TC of 1.2 Kelvin. It was rather hard to prove because aluminum has the TC of 1.21. Yep. So here also anti-bonding orbital plays a role. But these are complicated systems. Let's refer to something simpler. Heusler compound, which you can analyze like without referring to just simple chemistry, right? So Heusler compounds are composed, like in general formula, X, Y, 2, Z, where X is some kind of electropositive element, either mono, divalent, or trivalent, or maybe tetravalent. Y is usually an electron transition metal. Z is a log metal. Those crystal structures are related to some aristotles like tungsten and FCC copper, and their electronic structure bears the fingerprint of all those like aristotypes. Depending on what's put in the electropositive element, there might be differences in electronic structure. So, for example, Heusler alloys are only semi-conducting when there is a d metal at the X site because of the interaction. So a decade ago, Professor Michal has found several Heusler superconductors, palladium by these Heusler superconductors, and found that there's a large, like the largest number is found for 27 electrons per formula unit, and actually also having the same DC, which is disturbingly similar to what was observed by Matthiesen simple alloys, like SEC alloys. The molecular orbital picture for all those compounds is very similar. It has palladium to 8 palladium atoms forming a cage, which interacts with tin and yttrium, forming an anti-bonding PD2 SNP state at the Fermi level. Okay, so if we take the magical 27 electrons as our selection criterion, what new compounds can we find this way? So a pentavalent electropositive cation like niobium wouldn't work because there are no bivalent electronegative ones. 4-3 and 3-4 combinations are already all reported. So how about taking magnesium divalent cation and then something pentavalent like antimony? And it turns out it worked great. We found a new with a asterisk, a superconductor, new because we had a dispute reviewer who said that it was reported some years ago, which was like one line, not even line, one figure in a 2-page paper saying the unit cell parameter. But let's say it's new-ish. The preparation is kind of tricky. However, we were able to make it pure and superconducting. The nickel one cannot be synthesized for now, even though it's reported. Nevertheless, our anti-bonding plus electron count approach has worked. So how about replacing that further with lithium? It wouldn't work for back 27 because we would have to use like tellurium, which is going to form a electron charge transfer pair with lithium, forming a ionic bonded lithium to tellurium plus palladium. But if we decrease our expectations of valence electron count 25, it actually gives us a superconducting material, lithium, palladium to germanium, which is a very rare case of ternary type 1 superconductor. Okay? And again, density of states at the Fermi level is dominated by anti-bonding states. The silicon analog was actually predicted by our calculations. We found it after measuring it in helium-3. And to summarize, I hope I convinced you that we were able to map our tiny little neighborhood, but that's not the only superconducting materials and superconducting families in which the antibody populations plays a role. We have reported by our colleague Winiarski, by Jamie Nielsen, for example, and our recent paper, Rubidium Bismuth 2, in which we find that the relativistic effects or relativistic chemistry effects stabilizes the structure, prevents the distortion, but then it leaves the instability, leaves a footprint in the electron conducting. So thank you for your attention. I would like to thank my collaborators, thanks the funding agency, and thanks the organizer for organizing a great conference in that beautiful place. Sorry?
You mentioned that machine learning is useless
sorry.
advanced structure calculations, superconductivity, or
so advanced machine learning approaches for finding new superconductors are not particularly successful to date. So there are a number of studies, recent, and they either predict materials that are already found or are extremely similar to what was found, or they predict some kind of completely bizarre systems like a wideband like semiconductor that maybe can boot into superconducting state that would require pressures like 1 terapascal or something. So it's not like we don't know how to teach the computer to distinguish the superconducting from non-superconducting candidate. That's the problem.
More questions?
Yes, exactly. So
you cannot let machine learning work on 2, 3, 4, 5 examples. I mean, if you operate, they're all the same.
Exactly. Yeah. So as I said, there are like 10,000 of superconductors. But if you look in the superconductivity, like half of those reports are IPO or MGB2 somehow. So we are like the data is very grainy and it's very coarse. There is no. Also, the database itself suffers from the problems of early years, where the superconductivity report was just like 1-page paper, which said, I discovered superconductivity in 20 different systems with no figures, no, like sometimes even no TC. So that's one of the troubles here. Maybe we can fix that somehow.